My name is Ata Cizari. I'm PhD student at Biomedical Photonic Imaging Group of the University of Twente. The title of my presentation is Exploration of Movement Artifacts in Handheld Laser Speckle Contrast Perfusion Imaging. We have designed a handheld probe for laser speckle contrast imaging, which is able to perform color imaging and perfusion imaging. And because it's in handheld mode, we should tackle with the movement artifacts. For this reason, we have decided to employ an electromagnetic tracker to track the movements of the handheld probe during a handheld measurement. This video shows recording of so-called perfusion maps operated in handheld mode. And as you can see, some frames are unrealistic, which is due to the movement artifacts. Employing electromagnetic tracker, we were able to estimate on surface displacement of the beam, and that's what you see in this Lissajous graphing, which is shown in actual time. 10 healthy test subjects performed handheld measurements, and for each handheld measurement we were able to estimate the translational speeds in centimeters per second, tilt of the wavefront in degrees per second, and on surface speeds in centimeters per second. And for the distance from camera to the sensor of 20 centimeters, the average on surface speed is measured as 0.9 centimeters per second, and the average tilt speed is measured as 1.1 degrees per second. We hypothesize that the drop in the speckle contrast during a handheld measurement on a static surface is because of the applied on surface speeds and tilts of wavefronts, which is shown as a point cloud in this graph. In the second phase of our experiments, we used a motorized stage to mimic translational speeds and tilt of the wavefront by tilting the sample. And here we can model this problem by looking at each point being conjugated onto the image plane, which has some fluctuations on intensity basis due to the movements. And the frequency of these movements, which are driven by the optical Doppler effect, is a product of the applied speed and the subtraction of the incoming and outgoing wave vectors, the variation of them. And what we can say is that for each point there is a fluence distribution of incoming k vectors that contributes to these fluctuations. The yellow fluence distribution shows a sample of a rather higher scattering level, while the red one shows a sample of lower scattering level, so the light penetrates more into depths. And the higher the radius of this fluence distribution, the higher the observed frequencies and the lower the observed speckle contrast. Using this video, we can represent the speckle patterns while we apply translation and tilt, and we can also have a look at temporal fluctuation of observed speckle contrast versus the applied translational speed and the tilt speed. We continued our motorized experiments by measuring on samples of various scattering levels, and in both cases of translations and tilt, we can observe that as the scattering level of the medium decreases, the drop in the speckle contrast increases. We perform some in vivo experiments. This graph shows fluctuations of speckle contrast measured on forearm of a healthy subject. The first phase, when the system doesn't move, fluctuations of speckle contrast is mainly driven by the heartbeat of the patient. When the system starts to move, we can observe the same pattern, but in general, the speckle contrast follows a drop because of the applied movements. We used Midalgon cream to increase the perfusion level of the test subject, the same area. So by measuring on two different healthy test subjects, we have observed Speckle contrast drop as we apply translational speed before application of middle gun and after application of middle gun. Similar behavior is observed in both cases, and what, for instance, we can say is that when the system doesn't move, the observed speckle contrast after application of middle gun is way lower than that before application of middle gun. What we can conclude from this work is on surface speeds and tilt speeds are two measures of movement artifacts, and scattering level of the medium tends to play a role in creation of movement artifacts. This work has been published in Biomedical Optics Express. And I would like to thank you for your attention.